KURINJI Senior Secondary School, CBSE, Namakkal.
Successful result producing school in state every year.
Administered by the Board of Directors with over 35 years of experience in the teaching field.
Special attention on art, craft, music, dance, silambam, yoga, skating and karate.
Focus on Hindi Sabha and Spell Bee Olympiad exams.
Smart class for effective and innovative learning and well-furnished library.
Solitary importance on sports and games in state and national level.
WhatsApp facilities to know activities of students and school inside the campus.
Free bus for LKG to 8th standard.
Free, hygienic and nutritious food.
NEET, JEE, IIT coaching experts from Rajasthan and Andhra Pradesh along with our effective teachers.
Admission registration for classes LKG to +2.
Talent cum scholarship exam will be held on 14/4/2020 and 19/4/2020.
KURINJI Educational Institutions, CBSE and State Board, Namakkal.
KURINJI Educational Institution, Kavetipatti, Namakkal. Admission in progress. CBSE, KG to 12, contact 9025895176. Metric 6 to 12, contact 9344567484. For online admission, log on to www.kurinjischoolnkl.in.
In continuation to the last class, in this class we start with problem number 14. See here. The Earth's surface has a negative surface charge density of 10 to the power of -9 coulomb per meter square. Full stop. The potential difference of 400 kilovolts between the top of the atmosphere and the surface results in a current of only 1800 amps over the entire globe. Two things I told you, ma. So the first point is the Earth's surface has a negative surface charge density of 10 to the power of -9 coulomb per meter square. Second one is the potential difference of 400 kilovolts between the top of the atmosphere and the surface results in a current of only 1800 amps over the entire globe. One thing you just observe here, that is when we are taking the potential difference between the top of the atmosphere and the surface, see here we have to keep in mind, due to the low conductivity of the lower atmosphere, that is what the point we have to keep in mind while solving the problem. Okay, right. Now after completion of this, if there were no mechanism of sustaining atmospheric electric field, how much time would be required? Roughly how much time would be required to neutralize the Earth's surface? Okay, right. So what I am saying is here, observe carefully. The Earth's right. See, observe carefully, because why I am saying to observe means the entire problem we have to keep in mind at a time. What are the things they have given? What is the thing we have to find? I will repeat once again. The Earth's surface has a negative surface charge density of 10 to the power of -9 coulomb meter square. Next, the potential difference of 400 kilovolts between the top of the atmosphere and the surface, results in a current of only 1800 amps over the entire globe. Right. If there were no mechanism of sustaining atmospheric electric field, how much time would be required to neutralize the Earth's surface? So we have to calculate the time. Right. See here. See, first, surface charge density sigma is equal to surface charge density sigma. That is what already they have given. That is 10 to the power of -9 coulomb per meter square. 10 to the power of -9 coulomb per meter square. Radius of the Earth also given, that is already we know that is a constant value 6400 kilometers. but whatever the value they have given, that we have to take. Here they have given 6.37 into 10 to the power of 6 meters. 6.37 into 10 to the power of 6 meters. Anyhow, if you write the given values, one is surface charge density, sigma is equal to 10 to the power of minus 9 coulomb per meter square. Current I is equal to 1800 amps. Current I is equal to 1800 amps. Now, total charge of the globe. Total charge of the globe, Q is equal to surface area into sigma. Because sigma is equal to Q by A. Here, total charge of the globe is equal to Q is equal to total charge of the globe, Q is equal to surface area into sigma, that is equal to 4 pi r square sigma. 4 pi r square sigma. Now we are going to substitute the values, that is equal to 4 into 3.14 into r square means 6.37 into 10 to the power of 6 whole square into 10 to the power of minus 9 into 10 to the power of minus 9, that is what surface charge density. Surface charge density, that is equal to 509.65 into 10 to the power of 3 coulomb. So the mathematical calculation, this mathematical calculation will tell us, will give us 509.65 into 10 to the power of 3 coulomb. Right. Now required time T is equal to Q by I, that is equal to 509.65 into 10 to the power of 3 divided by 1800, that is equal to 283.13 seconds. 283.13 seconds, that is approximately or roughly 283 seconds. 283 seconds. So what is this 283 seconds? This is the time. This is the time which would be required to neutralize the Earth's surface. This is the time which would be required to neutralize the Earth's surface, that is 283 seconds. Next problem, that is problem number 15. Right. Before going to discuss the problem number 15, once if you look at the problem number 14 orally, see, because of having the surface charge density and current value and radius of earth value, we calculated the total time taken, the total time required to neutralize the earth's surface, with the help of the formula Q is equal to sigma into A, and then the formula T is equal to Q by I. Okay, right. Q is equal to IT. Q is equal to IT, right. Next problem number 15. In the problem number 15 there are two things, A and B. So you please observe carefully, and first we will discuss A and then we will come to B. Right. A. 6 lead acid type of secondary cells. 6 lead acid type of secondary cells, each of EMF 2 volts and internal resistance 0.015 ohms are joined in series to provide a supply to a resistance of 8.5 ohms. Right. Now the thing is, what are the current drawn? What are the current drawn from the supply and its terminal voltage? What are the current drawn from the supply and its terminal voltage? Right. So two things we have to find. One is current, another one is terminal voltage. Okay. See, going back to the first sentence. 6 lead acid type of secondary cells. 6 lead acid type of secondary cells, each of EMF 2 volts and the internal resistance 0.015 ohms are joined in series to provide a supply to a resistance of 8.5 ohms. Full stop. What are the current drawn from the supply and its terminal voltage? Now see here, first we will discuss A and then we will come to B. Now question completed. No, see here, epsilon is equal to 2 volts, that is what they have given, and then internal resistance small r is equal to 0.015 ohms. Then R is equal to 8.5 ohms. Capital R is equal to 8.5 ohms given. Next, N is equal to 6 because clearly mentioned 6 lead acid type of secondary cells. That's why N is equal to 6. When the cells are joined in series, according to the question, he is saying that are joined in series. So when the cells are joined in series, the current is I is equal to N epsilon divided by R plus NR. So this is the formula we got when we discussed the cells in series and cells in parallel. Right. When the cells in series, I is equal to N epsilon by R plus NR, that is equal to 6 into 2. 6 into 2 divided by 8.5 plus 6 into 0.0015. 8.5 plus 6 into 0.015, that is equal to 12 divided by 8.59 amps, which is approximately 14 amps, which is approximately 14 amps. Right, see here. If you complete that mathematical process, here we are getting this is here we won't get 14, it is 1.4, right. So 12 divided by 8.59 will give us 1.4 amps. It is not 14, it is 1.4. Now terminal voltage V is equal to IR. See, already here we have I value, that is 1.4 amps, and R value given, that is 8.5. So if you multiply these two things, mathematically we are getting 11.9 volt. 11.9 volt. Okay, right. Now see here B, right? B. A secondary cell, see A completed, no? Now B. A secondary cell after long use, a secondary cell after long use has an EMF of 1.9 volt and a large internal resistance of 380 ohms. A secondary cell after a long use has an EMF of 1.9 volt and a large internal resistance of 380 ohms. What maximum current can be drawn from the cell? What maximum current can be drawn from the cell? That is the question. And in continuation to that, could the cell drive the starting motor of a car? Could the cell drive the starting motor of a car? So one is asking to calculate maximum current which can be drawn from the cell, and the other one is could the cell drive the starting motor of a car? Two things we have to find. Now you come to this point, that is first we have to write the given values, that is EMF epsilon is equal to 1.9 volt and internal resistance small r is equal to 380 ohms. Now I maximum current, so it is like Ohm's law, no? I is equal to V by R. So I maximum is equal to epsilon by R, that is equal to 1.9 by 380 amps, will give us 0.005. This is what 380 ohms, not amps, 380 ohms, it is volt. Finally we are getting 0.005 amps. Okay. Now see, one more question is there, no? One more question means what? Continuation to that. Could the cell drive the starting motor of a car? Right. So what can we say? The secondary cell cannot drive the starting motor of a car because that requires a large current of about 100 amps for a few seconds. See, basically to start a starting motor of a car, okay, to start motor of a car, we need a current in terms of 100 amps for a few seconds, but here how much current we got? Just it is 0.005 amps. So when compared to 100 amps, this 0.005 amps is very less. That's why it is not possible. So that we cannot drive the starting motor of a car with this current. With this current, what we got? 0.005 amps. So what can I say? This secondary cell cannot drive the starting motor of a car because that requires a large current of about 100 amps for a few seconds. Right, next problem. that is 3.16. Okay, that is 3.16 means a chapter name is current electricity, no? That is third chapter and 16th problem. Right. Anyhow, next problem, that is 16. See here. Two wires of equal length, one of aluminium and the other of copper, have the same resistance. Which of the two wires is lighter? Hence, explain why aluminium wires are preferred for overhead power cables. It's a very interesting question because it is application to daily life. You know, when we go for field and sometimes within the city also, you can see high tension wires which carries electric current from that source of energy, means that is what electric power station, where the electric power is going to generate, from generating station to the substation which is just outside the mandal headquarter or district headquarter. So which are high tension wires, HT wires. You can also call them as power cables. So generally, because of having those things on the top of us, we are calling them as also overhead power cables. Right. So here regarding that application, what is the problem? Two wires of equal length, one of aluminium and the other of copper, have the same resistance. This is the information given. So length is equal and resistance also same for both aluminium and copper. Which of the two wires is lighter? That is one thing. And then which of the two wires is lighter means what we should do? We have to find out the masses. Otherwise, we have to find out the mass ratio of copper to the aluminium. Then we can come to the conclusion which is lighter. Otherwise, we can't. Okay. In continuation to that, hence explain why aluminium wires are preferred for overhead power cables. Okay. And to solve this problem, they also given some values, that is aluminium. For aluminium, it is 2.63 into 10 to the power of minus 8 ohm meter, and for copper 1.72 into 10 to the power of minus 8 ohm meter. Relative density of aluminium is 2.7 and relative density of copper is 8.9. Relative density means what? Density of a substance to the density of water at 4 degrees centigrade. So relative density is the ratio of density of a substance to the density of water at 4 degrees centigrade. So that is relative density, and it is for aluminium 2.7 and for copper it is 8.9. So these values also part of question and given values. Now see the answer. Density is equal to mass by volume. We know mass is equal to density into volume. Otherwise volume into density, right? That is equal to ALD. See here, that is equal to rho into L by R, because you know LD is as it is. You know, R is equal to rho into L by A. R is equal to rho into L by A. A is equal to rho into L by R mathematically. So rho D, already L is here and one more L. So L square by R. Rho D L square by R. Now mass ratio MCU by MAL. So that is for copper to the aluminium. And one more point here I want to remind you, that is whatever they have given, that only I want to remind. As of the two wires are of equal length and have the same resistance, then these two we need not to consider. No, this one and this one need not to consider. Only these two are the major factors which decides the mass ratio. That is the reason here we have only rho and D. Okay, rho means what? Specific resistance or resistivity. Okay, mass ratio MCU by MAL is equal to rho Cu into dCu and rho Al into dAl, because rho d both are in numerator. So mathematically also, to get a mass ratio of copper to the aluminium, here it is rho Cu divided by rho Al into dAl, that is equal to 1.72 into 10 to the power of minus 8 into 8.9 divided by 2.63 into 10 to the power of minus 8 into 2.7 is equal to 2.1558. So which is approximately equal to 2.2. So what is our conclusion based on this mass ratio, right? So which is lighter and which is heavier and how many times? See, copper wire is 2.2 times. Copper wire is 2.2 times heavier than aluminium. Copper wire is 2.2 times heavier than aluminium wire. Since aluminium is lighter, it is preferred for long suspension of cables. Otherwise, heavy cable may sag down due to its own weight. Okay. So that is the reason. So what is the reason? Because of light. So which is light? Aluminium is light when compared to copper. That's why we prefer copper wire. We prefer aluminium wire. Suppose you can use copper wire also, no problem. But it is more, no, it is 2.2 times heavier. Because of its own weight, it sagged down. So when it sagged down, because it carries high power, no, so it is a big problem. That's why because of light, we preferred aluminium when compared to the copper. Right, next problem, that is 17. See here. What conclusion can you draw from the following observations on a resistor made of alloy manganese? Okay, what conclusion can you draw from the following observations on a resistor made of alloy manganese? Right, see the table. Okay, current, voltage. See which is what 0.2 and 0.4, 0.6, 0.8, 1.0, 2.0, and here 3.0, 4.0, 5.0, 6.0, 7.0, 8.0. Right. See the regarding voltage values. For 0.2 it is 3.94, 0.4 it is 7.87, and so on. So they have given current values and respective voltage values. Right. Okay. Now what he is asking? He is asking the conclusion which we have to draw from the following observations on a resistor made of alloy manganese. Okay. See here we are going to draw a graph. We are going to plot a graph. We plot a graph between current. That is what current is along y-axis. No, current is along y-axis. Okay. Then you can see here which is what current and this is what voltage. So we have taken current along y-axis and we have taken voltage along x-axis. So by taking current on y-axis and voltage on x-axis, we plot a graph. See here. So this is the curve we got. And these are the points. Right. See, from this graph, what can we conclude? Means, I will tell you, you just listen carefully. I didn't write the information here, but I am saying orally. See here. Since the VI graph is almost a straight line, we are saying, no, this is the straight line. Since the VI graph is almost a straight line, therefore, manganese resistor is an ohmic resistor for given ranges of voltage and current. Right. See, I already told you what is ohmic resistor and what is non-ohmic resistor. So, which follow Ohm's law, which is said to be ohmic resistor, and the graph for ohmic resistor will be like this. That is the straight line passing through the horizon, right? So that's why, because of the straight line what we got based on the given values, so the alloy manganese is a ohmic resistor, right? Now, as the current increases from 0 to 8 amps, the temperature increases, but the resistance of manganese does not change. The temperature increases, but the resistance of manganese does not change. This indicates that the temperature coefficient of resistivity of manganese alloy is negligibly small. This indicates that the temperature coefficient of resistivity of manganese alloy is negligibly small. So we are saying 3 points. One is alloy manganese is a ohmic resistor. Second one is as the current increases from 0 to 8 amps, the temperature increases but the resistance of manganese wire does not change, which indicates that the temperature coefficient of resistivity of manganese alloy is negligibly small. So finally 2 points we are drawing. One is alloy manganese is a ohmic resistor, and the second point is the temperature coefficient of resistivity of manganese alloy is negligibly small. Okay, right. So in this class we discussed 4 problems, 14, 15, 16 and 17. So next class we will continue to start with problem number 18. Okay, thank you.